Hello and welcome to the next video on how to evaluate limits. Today we're going to evaluate the limits of rational functions. So you might ask, what are rational functions? Well, rational functions are functions where you have a function in the numerator and a function in the denominator. And that's what we have in these three questions today. Not only that, if you compare the numerator and denominator in these three questions, you will notice a pattern, and that is the degree of the numerator is always lesser than the degree of the denominator. And hopefully after going through these three questions, you should be able to see a pattern that will help you to evaluate limits of these types of rational functions next time. Okay, too much talking, let's get down to business. Part A, how do we evaluate this limit of this expression, limit of 1 over x minus 1 as x approaches infinity? Now, this is very similar to what we did in the earlier video, question 1D. Now, if you recall in 1D, this is what we found, right? We found the limit of 1 over x as x approaches infinity. We found that to be 0. How we got that was we substituted larger and larger values of x into the denominator. As the denominator got larger and larger, the entire fraction becomes smaller and smaller, right? And that's how we got 0. Using the same line of reasoning, we can say that as we substitute larger and larger values of x, 10 million, 1 billion, 100 gazillion, right? The negative 1 becomes quite insignificant. In fact, it can become negligible, right? As we approach larger and larger values of x. So this thing is going to approach 0. Yeah, because we're just going to get a huge denominator, and then the answer is going to be really, really small. Okay, nice and easy. Now let's look at part B. So for part B, we have a more complicated expression, but if you notice carefully, the denominator can be factorized. So I'm going to do that. In fact, you can see it's a difference of 2 squares. So let's write that down as x plus 1 into x minus 1. Okay, and when you have a product of expressions in your denominator, you can use partial fractions to split them up. Okay, so if you did partial fractions, which I've done ahead of time, you're going to get this 1 over 2 into x plus 1 plus 1 over 2 into x minus 1. Okay, and I'm going to make things easier. I'm going to factor out the half. So you have 1 over x plus 1 plus 1 over x minus 1. And straight away, you can see 1 over x minus 1. This is going to approach 0 as x becomes larger and larger. We just did that in part A. All right. And if you look at this one over here, right, it is the same thing, right? As x becomes larger and larger, x plus 1 becomes larger and larger, then this whole fraction is going to go towards 0. Okay. So inside the bracket, I have 0 plus 0. Then you know what? This whole expression is going to approach 0. Okay, so the answer for part B is also 0. Now, before I move on to part C, you might want to pause and try this yourself. Okay, the approach is quite similar to part B, where you have to factorize your denominator and then go by partial fractions. Are you ready? Let's go through the solution for part C. Now, first of all, you can see the denominator is a difference of cubes. Difference of cubes can be written this way: linear times quadratic, following this rule. SOAP, same sign, opposite sign, always positive. Yeah, same, opposite, always positive. X minus 2, x squared plus 2x plus 4. So let's write that down, part C, with its factorized denominator. This is going to be x squared over x minus 2, x squared plus 2x plus 4. And okay, if you do partial fractions, which I did ahead of time, of course, so that this video wouldn't be too long, what you get is you're going to get half and half again, right? So I gone ahead and just factorize it first. Okay, and you should be very comfortable by now to say that this will go towards 0. And I don't even have to explain why. Yeah. Now let's look at this one. This one is not so straightforward because the denominator cannot be factorized, right? Or it cannot be factorized. Yeah, it cannot be factorized. There's no real roots, right? Okay, then how do we evaluate the limits of this thing, right? That's where you have to do a bit of thinking. Say if I substitute a large value of x, say 10 million, right? If 10 million is over here, then my numerator will be 10 million. But how about my denominator? I have an x squared over here, which means it'll be 10 million times 10 million. There'll be like 14 zeros, right? I have 14 zeros plus 20 million plus 4. This denominator is going to be much bigger than the numerator. In fact, as I increase the number of zeros, as x becomes larger and larger, bigger than 10 million, the bottom, the denominator, will grow much faster than the numerator. Okay, and for this exact reason, I can say that this will approach 0. Okay, so if that approaches 0, then this whole limit is going to approach 0. Okay, in fact, the learning point from over here, from this, is going to apply, right, to all proper rational functions. So if suppose we have a rational function, let's just look at, say, quadratic in the numerator, right, over a cubic, for example. Yeah, the limits of this expression as x approaches infinity is always going to be 0. And we've seen why that happens, right? Just one more time. Why that happens is because if you substitute a huge value of x, yes, for example, 10 million, then your numerator will be somewhere around 10 million square, which is 14 zeros, right? 14 zeros. Okay. But let's not forget, in your denominator, you will have 10 million to the power of 3. That is 21 zeros. Okay. And as we increase the number of zeros, as x becomes larger and larger, like 100 billion, 10 gazillion, right? What happens, right? The number of zeros at the bottom is going to be much more than the number of zeros in your numerator, right? That's the way it's going to be, because it's an x cube and your numerator is only x squared. And that is why we can safely say over here that the limit as x approaches infinity of proper rational functions is always going to approach 0. Okay, and that is an important result. I come to the end of today's video. I hope you enjoy watching. I hope you learned something today. And yeah, until the next video, catch you on the flip-flop.